Dear participants, in a while we are going to stream live on YouTube.
Am I audible?
Yes, yes.
Okay. A very pleasant afternoon to all. Honorable Resource Person, Dr. Mahesh Srivastav, respected dignitaries of MES and PSCSC family, the organizing team, the galaxy of intellectuals from all over India, my dear colleagues and students. On behalf of our institute, Pillai College of Arts, Science and Commerce, Rasayani and IQAC, we, the team, are delighted to offer a gracious welcome to an international webinar to mark and celebrate World Environment Day, aiming to create awareness about the paramount significance in our lives during this current situation of COVID-19 pandemic. It is said the most important seed you can plant is education, and the most valuable crop it yields is enlightenment. Well, the light of Dr. K. Vasudevan Pillai is one of such examples. As the founder CEO of Mahatma Education Society, established in 1970, Sir has built 48 institutions from national and international schools to colleges of arts, science, commerce, architecture, engineering, management, media studies, vocational education, and teacher education. With combined efforts taken by our honorable founder, Dr. K. M. Vasudevan Pillai, and co-founder, Dr. Daphne Pillai, the seed of education planted by them has been expanding, and today it has presence in every important aspect of education. It gives me an immense pleasure to certify that NES is celebrating its 50th successful year, a dream nurtured by our upstanding founder, guided by our principal, and supported by over 1,500 dedicated staff members. And I'm honored to be a part of IQAC family. Our institute is organizing this webinar as a part of the series of talks to mark the Golden Jubilee year of Mahatma Education Society, entitled Seismic Environmental Hazard Predictions and Challenges through Google Meet, and it is streaming on our YouTube channel by parental body NES live to accommodate more participants. Barry Commoner quotes, the proper use of science is not to conquer nature, but to live in it. And we have such persona amongst us today who lives in it, whose research in environment is commendable. It's my pleasure to introduce our resource person for the day, Dr. Mahesh Srivastav, who is presently working as an assistant professor at Northern Catholic University, Chile, South America, and other investigator at National Research Center for Integrated National Disaster Management. His primary field of research line is in physical and natural sciences, well known as earth sciences. Sir has been actively working for programs like FONDAP and FONDASITE in various research projects as postdoctoral, principal investigator, and co-investigator over the years. He has 8 years of experience in research and is still pursuing his passion tirelessly. Sir has also supervised and supervising thesis of doctorates and postgraduates. Sir holds numerous publications in journals categorized as ISI publications, non-ISI publications, and congresses, focusing on issues such as earthquake, cosmic displacement, and tsunami. It's a privilege to have Dr. Mahesh Srivastav with us all today, and I'm looking forward already to the unfoldings and learning nature again with a new perspective. And may I request our speaker, Dr. Mahesh Srivastav, to honor this virtual dais and interact with you all. First of all, let me thank him for accepting our invitation and making himself available for this particular interaction. So thank you so much, sir, and I would like to come on board and interact with us all. Thank you. Over to you.
Okay, thank you for my little bit information. So may I start now?
Yeah. Yes, sir.
Okay, just I'm sharing my slides. Okay, everybody is able to see this my slides? May I start?
So I think your slide has not been shared. We're not able to see.
Yes, sir. Right now it's on.
Okay, just a minute. I think it is visible now.
Yes.
It is visual now. May I start now?
Yes. Yes.
Yes, sir. Please go ahead, sir.
Okay. Thank you for the this opportunity to present my work, and I think it is very, very important for understanding our environment and how we can use our scientific knowledge. And particular, I am working for the earthquake and hazard assessment. So it is very, very important to utilize this type of information towards for the safe environment. So if you know that there are several types of disasters, like sometimes it is a flood, sometimes it is rain, sometimes a lot of fires, sometimes landsliding, and earthquakes and tsunami. So seismic hazard, and it is like a part of the one impact which is directly related for the environment. So generally, earthquake it mostly occurs in the subduction zone, in the boundary of the plates. But if sometimes earthquake also takes place on the plate, like a continent. Like sometimes you can observe it occurred like a Latur earthquake in Maharashtra. Sometimes it occurs in like a Bhuj earthquake. So it is very important to understand all the physics of the earthquake, how earthquake takes place, and how we can like understand how we can be safe for we can make our like understanding better for the better way to live proper and safe. We can if you understand the physics, if you understand the proper hazard, you can be safe. You can feel like, oh, we are living in a safe environment. So like in Japan, it is very big earthquake used to come, but they follow some tricks. They understand the physics of the earthquake, and they understand like, okay, now earthquake is going after, what need to do? For this, people feel, okay, this is the way earthquake is like, it comes like this, and how we have to behave with this disaster. And we cannot stop the disaster, but we can be safe. We can be like we have to survive in the best way. So now I would like to explain what is the general we are working here, and how this seismic hazard used to take place, and how we can like survive in this type of thing. So before that, I would like to go for what is the earthquake. Sometimes just we feel shaking on the crust, on the earth, because we say in the geological and geophysical phenomena, oh, this is the vibration on the crust. But people say, okay, we are feeling some shaking on the surface, and this shaking of surface, it comes from some points, and this things takes place inside the earth. And it may be 5 kilometer, it may be 50 kilometer. If it is the silo, means if it is 2 to 5 kilometer, we can say it is silo depth. And if it's a center source is from down depth, then we can say it is a very like a deep, and its effect would be the very less. We can observe very small tremors, sudden shaking, it will be very small. So some shaking on the surface due to some cause, like it may be the earthquakes, and sometimes earthquake is not only sources, there are some nuclear tests. Sometimes you can have the reservoir induced seismicity also, like if you have any dam nearby, and sometimes with loading, unloading, it can provide also some shaking. So, but here we are going to discuss only related to earthquake. We generally we say seismicity, like seismic events. So once some shaking, but this shaking generally takes place due to some sources. Where is source? Source is under the earth, and this source it comes through the seismic waves. It has P wave, S wave, and it can provide some shaking on the surface. Here we present like where is the epicenter, where is the hypocenter. So generally where earthquake takes place in down the earth, we say it is the focus of the earthquake, and sometimes people say hypocenter. And where on the surface, we observe, okay, this was the points down the earth, earthquake had taken place, that point say epicenter. So how, but when we see the for the normal person, people who is not knowing the earthquake, it is important to know that earthquake is not a one point source. It occurs in one plane, and sometimes it can be very complex fashion. But generally for the scientific purpose, we try to model as a plane, like a earthquake has. So now we say earthquake has initiated from particular points, and then it propagates in the particular. It may be rectangular, it can be square, and once it occurs in plane, we can estimate, okay, this how the displacement, like we observe the surface, how much displacement has taken place. For this, we have several very good instruments like GPS, and sometimes we use the INSAR for identify the displacement, horizontal as well as vertical. And this is very, very important for the numerical modeling to understand how energy has released, because then you will say how this energy accumulate. Then for that you have to go for the another like plate tectonics theory. Then I will explain both some aspect of them. So now we have to understand how many types of earthquake we have. Generally we have mainly two types of earthquake: interplate earthquake, intraplate earthquake. Like sometimes when earthquake occurs, so it generally occurs between the boundary. Like for that you have to understand what is plate tectonic plates. When you understand plate tectonic plates, plate tectonics boundaries, like how many plates is there, what is the velocity, like a moment of particular plates, and on the basis of this you can understand what is the plate velocity and how much time it took taking for the earthquake. On the basis of velocity and its interface information, like a coefficient of rigidity, and then you can predict, but you cannot predict time. You can identify, okay, this region is going to be have big earthquake, and this is very, very important, because you know that Richter scale has come 1935, and our scientific seismic hazard research with instrumentally around 50 years, it is working on very well, and we are able to predict the where earthquake is used to come in the interplate earthquake, generally in the subduction zone. But it is very difficult to identify when it's going to have the earthquake, because we don't know how we can still we try several techniques, like before earthquake we have several gases radiation, like if you are breaking anything, like any stick or any pen, you know only you are pushing the forces, but you don't know when it's going to break. But in the case of earth also it's same, but you can use some technique to identify some radiation. If you observe some radiation on the surface, what is going to happen, then you can say. But problem is also there. If some radiation is started, but that it could not break fully, and it's only inside it's a nucleation process before the earthquake, and this nucleation process can take, it is 10 years. So it is very difficult. If I say, oh, radiation is very good, like you measure with the quantity, okay, some like 10 some balloon and unit balloon, 20 unit balloon, but it depends. Sometimes your interpretation may be wrong, sometimes it is good, correct. So for this, we need more best instrument to identify those things, but it has limitation, because interplate earthquake, generally earthquake comes in the sea and down the water, but intraplate the earthquake, like a Bhuj earthquake, like we know Latur earthquake, Koyna earthquake in the India, and any part of several earthquake, crustal earthquake on the plate, it used to come. But problem is where earthquake is going to occur, because if you have like a Bhuj earthquake 2001, Latur earthquake 1993. Now, if you want to identify on this fault when earthquake will come, so you have to understand what is the recurrence interval of the earthquake at particular fault. Like Bhuj earthquake, it was 7.7, and Latur earthquake 6.1. But if you go for the recurrence interval, its recurrence in more than 500 years. So now, if you start research now, you are going to get result 500 years after. Then this is the big problem in the earthquake, because geological process, it works very, very slow. And if you know like how much velocity of the plates, it is millimeter to centimeter, like our nail grow. Like if you don't cut your nail, you can see how much velocity of nail grow, and sometimes your hair grow also. So this is the velocity of plates. And if you want to use this information for long time, so you need long time information. So then you can do for long time research, then you can identify. But still we have GPS, INSAR, we use 10-year data to identify which region we get we are getting more accumulation of energy, and we can predict this with the historical earthquake, because we need the historical information also. Then we can suggest, okay, on this fault, on this region, earthquake may come within these years, this much times, but we cannot tell when earthquake is going to occur. This is our limitation. So we have two types of earthquake: interplate, intraplate, and second is anthropogenic events, like sometimes reservoir induced seismicity. Generally, we have a earthquake in the Koina, and if you know that Oroville earthquake 1975, it was first reservoir induced seismicity people have identified, because when it is if you have any big paper, if you put something and it start stress in downward, and suddenly when you are reducing the weight and it want to go an initial state, sometimes people identify that when you put any material on the surface, it starts it is elastic material, and when your mass is more than the capacity of this material, automatically it can break. And if its capacity is less, it can break. If capacity is not sufficient, it cannot break. So in the region, in the case of the Koina, and after when it was fully after the monsoon, when it full, after that, when it reduced, after in September, October, it start to reduce the water, vaporization and using. Then when it start to wants to come initial stage, it become like a change. If you put the water and it's the shape change, and suddenly if they are unloading effect and start to go an initial state, that time it broken and it provides a 6.1 magnitude earthquake. Sorry, 6.7. So it was around 200 people died and 1,000 persons were injured. Because this type of things is very, very important to understand. People should identify what is the strength of that region and how much water it can, how much water it can sustain. So it is very, very important to understand this type of seismicity. Sorry, it was so okay. So now, is it visible? Anybody can tell me?
Sir, the slides
Yes.
are visible, but just that it is not in slideshow. It's not covering the entire screen.
Okay, just. So whenever you people don't get it, please tell me.
Definitely, sir.
Okay, now it is okay. It is okay now?
Sir, you are going to explain the sixth slide, difference between magnitude and intensity of the earthquake?
Exactly.
Okay.
Okay, so now this is the like in for earthquake, we are going to explain another point, magnitude and intensity. So for the magnitude, it is uniformly people using all over the world. It is the seismic moment, and this is like if you know the region, you have to understand how much big earthquake, like any earthquake has occurred. So you are using some plane, and that plane you have to identify area and how much erroneously and what is the rigidity of the region. Then you can get how much seismic moment, and this seismic moment people use everywhere same. But in the case of the intensity, it is different, because if earthquake is coming 2 kilometers down in the silo, so it has more shaking, so it can more damage. If earthquake is coming down more than 50 kilometers, it is same magnitude, same seismic moment, but its shaking would be less. So it has different you cannot observe much shaking. That intensity, it depends on your site. So there are several parameters to use the for understanding to intensity of the earthquake. So for the intensity, we don't have any uniform system like in the case of this Richter scale, we can measure the magnitude of earthquake, but intensity we have several. Every country using different intensity meter to identify it. Like in India, we have Mandiu, Isponier, Cornic scale. People say Yamas scale, and USA use modified Mercalli scale, and Japan also use the GMA seismic intensity scale. But I think it depends upon the shaking. So its range starts from 1 to the 12. But in the seismic moment, it magnetic moment, moment of the earthquake, people identify from 0 to the 10. And when 0 means nothing, after that it should start. So 10 is the maximum. It is logarithmic scale. So if you have seismic moment 6, it is equivalent 10 of 5. And if you go for like a magnitude of 6 is equal to 100 times the magnitude of 4. Like if you have 9 magnitude earthquake, 1, it means 8 magnitude is 10 magnitude and 10 magnitude of 8. So it is logarithmic scale. It accumulate more energy when you increase 1 magnitude. So here again we are going to go for more depth. So in the earthquake, generally earthquake doesn't come everywhere. Why? Because it has to slip somewhere. So for that it works on the particular fault. In the subduction zone, the people identify this is the interface where subduction is going on. That mega thrust, we say mega thrust, is a interface. So where an interface, generally earthquake comes, and only earthquake occurs until the 70 kilometer. Why? Because only during the plate tectonics and collision, energy can accumulate and that depth. Because after that you have temperature very high, and this is viscous material. It cannot sustain mass like a more stress. So in this case, you have only earthquake 60-70 kilometers. Like if you see any global earthquake, you will have earthquake until the 60-70 kilometers. So why? Because it is most elastic and it can accumulate energy and it can release with earthquake. So once you have fault zone, so you can identify what is the strength of this fault, how much big earthquake can occur in particular this fault. So we have here heterogeneity like a slab, we can say it is the subduction zone earthquake type, and this is damage. This is the like a crustal fault we can observe in the case of the Latur earthquake, Bhuj earthquake, and Koyna type. And we can use the, because earthquake occurs in the down in the earth. So we use this information and we can model it, because we don't know, we cannot see it. So we just take some signals from there. Sometimes people use the seismic signals like seismic wave, and we use the displacement. And we use the GPS displacement. We can observe what happens in the. We can model it. What is the happening in particular places, and after that we can model how much ground motion is there. And it is reverse also. If you know ground motion, you can model the rupture like fault structures, and if you have fault structure, you can model forward model, you can get the shaking. So this is the rupture process. Another one, how this plate tectonics function. So we have like a whole earth, and it has 3 layers, like a crust, mantle, and core. And core, internal core is solid, and outer core is liquid, and mantle is like a viscous, like a not pure solid, not purely liquid. It is viscous liquid. And upper crust, it depends. It until the 60 kilometer is more elastic. After the viscous material is increased. And what in the outer core and inner core, solid core, like inner or outer core, temperature is very high, and it start convection. And when convection starts, so some places it has ridges. You can see in the figures, it has a spreading ridge, and another place it is subduction zone. So what happens? This magma start to come on the surface, and it has like ridges and fracture zone. And generally it occurs in the sea. And when it starts to come on top, and it like become the piles, and it forces away. And we say it is rigid, and due to the gravitational potential energy, it pushing out towards the away. Once it is away, another region subduction, it goes down. So this is the forces we get from the plate tectonics. So it is the source. It is going to like a support for earthquake, like a mountain build-up and volcanic eruption. This is the pure physics. Once you have the volcanic eruption and some cracks there, like rigid, and magma comes, and this is the high magma because its density is down, it's very high, and when it comes from on like a top, and it start to deposit in the sea, and its density is very high and pushing outward. And once in the subduction zone, it goes down. Like if you see the any like a Sumatra region, Japan region, Chile region, Cascadia, so you have like a oceanic plates goes down. Why? Because its density is very high, and spreading was from the ridges. So that's why we have one places or you have oceanic plates. Another places we have continental plates. So like a Chile, you have South American plate and Nazca plate, Pacific. It's subduct. In the Japan also, we have like a Eurasian plates. It is a junction of 4 plates. Japan has 4 plates junction. So it is very, very like a seismically very active. It has Pacific plates. So it doesn't like a you have like a other plates also. Like you have continent collision, like a Himalaya. So in this case, you can like have the continental collision. You have less earthquake and big mountain like a buildup. So here we have one example of continental drift. So because it is with the geological time scale, it provides big like a deformation. And in beginning, people have identified that it was once together, and it start to separate this continental drifting due to the magma convection. So in how it can verified, it is verified with the fossils. If you see the South American and this is the Africa, and this is India. If you identify the course, you take the course and slide, and you can have the same type of fossils in the region. Here you have Antarctica, Australia, India. You can verify, okay, this plate tectonics is correct. So now, yes?
Sir, one. We are only, I think we are viewing only one screen, one slide, sir. I think you are not.
No, I have only one.
Okay, you are at the 6 slides. Okay.
Yeah,
Okay. Fine. It's fine.
is it visible?
Hello.
Okay.
Just
No, sir.
to just
Are you able to see this?
yes, sir. We
No,
are able
sir.
to see.
Sir, no, sir.
Yes, sir.
Right now you have changed, sir.
Yes, sir. Yes, sir.
अभी दिख रहा है.
Yeah, correct. Okay, correct. Now it is visible. If you don't see it, please tell me. I can open it. Okay.
Please, sir, keep changing
If
the
we
slides.
see
Also.
the, it is okay.
Yes,
Yeah,
sir.
Correct. So if you will see the big earthquake and the global, all the seismicity we plotted, we see like this. But it seems like a random, but it is not random. If you see the earthquake was in the boundary of the plates. So if you see here, you have Indian plate and Indian Ocean plate, you have Eurasian, here South American plate. So and same time you have several plates, it has different velocities. And where you can observe with the okay, in which velocity is moving which direction, and with the using of the geodetic technique, you have INSAR, you have GPS, you have Doppler, so you can identify the velocity, on the basis of you can understand how much energy accumulating. So here we have one picture like how subduction zone behaves. So its velocity, one plate is going down, it is the oceanic plate because its density is very high. And here we have the continental plates, and we have coast here. We are just living on the top. And but we have here from it is trench, people say trench, where the two plates have meeting. And then you can see that here it is the long coast, it is ocean. So earthquake generally takes place here because this place, the most of the energy accumulate in this region. And what happens due to elastic body, it does not support for sliding, and it accumulate continuously, and it was energy sufficient to break the it is more than the friction, it is like friction. You have something forcing sliding any particle, and once your force is more than the friction, it can slip, and once it can slip, you will have earthquake and you will feel the shaking on the surface. So now you can see the here we have some a GPS constellation and geodetic, and how it works with the satellite. We have some GPS network on the basis of we have rupture here, we can identify some which is the model oceanic plate going down, and we have a continental plates, and the continent we have several GPS site on the and we can receive the GPS satellite signal, and we can get the what is displacement on the surface. On the basis of this, we can identify where earthquake has occurred and how much energy has released. So here, we know that last century, 20th century, 21st century, we have several big earthquakes. You can see that 9.1 2011 is by the 9.4 2004, and it is a Kamchatka region, and we have the here in the India region Eurasian Indian plates, and here collision. And we don't have big earthquake because it is continent, and elasticity and strength is not much to sustain more energy. So it is very good for the us, and it cannot have the earthquake bigger than 8. But people say sometimes people want to take attraction. Oh, this region can have earthquake 9.5. No, it is not possible in India region. It need to be very calm, cool. Earthquake may not go more than 8, maximum 8.5. That's that much. And but earthquake generally occurs in the coastal, in the sometime intraplate, it is little bit dangerous, and people should be very careful to identify the faults. Here I am trying to explain a little bit about the earthquake mechanism. Like here we have slab, like a subduction zone. One plate is going down, and one plate is going.
Sir,
It is, yeah,
sir, are you talking about the slide number 11?
yeah, 17.
So we are not able to see the 17, sir. We are at 11 only.
I think it is sometime it hangs.
Play the current slide. Okay.
It is correct. Earthquake mechanism.
Yeah,
Yes.
18. Yeah.
So,
So please
yeah.
keep
So in the,
slide.
yeah. So in this, if you have earthquake generally occurs in the interface of the plate. So we have oceanic plate, subductive oceanic plate. We have overriding plate. So generally earthquake occurs in this region. And in the crustal fault, you have like two plates, and sometimes strike slip, sometimes up and down. So you can make this simple model, like you have one block and you have a spring. Just you are pushing this. Once you start pushing, what happens? Until the some limitation, it can sustain, like survive. But if your forces is sufficient and like more than the friction, it start moves. And once it moves, we get the some patches, like some surface which has slipped. So similar way we can get on surface on this, like this fault patches, it has slipped. So this is the simple model to explain the earthquake. So we have what happens? You have block, you have normal stress from the top, and we have like one surface. And once you start the forces, like sometimes you can get from forces from the tectonics, forces, and it start slip. So this is the very simple model for explaining the earthquake. Now you can have the more better, and if people say it is elastic rebound and sticks with behavior. Like if you have any part like a point, like a slab, and if you want to push it in beginning, it will not allow because it's friction. You have normal stress and it will not move. And when you have here in first case, it will start the stress here. And once your forces is and beyond the it's a resistive forces, like you have normal forces and friction. It once it beyond this, and it will start slip. And here your stress is increasing with like you are pushing. Once it is more than the frictional forces, automatic it slips. Once you have another, people say it goes in another cycle. Once earthquake occur, again it needs some similar time. So here you can see from here to here how much time is there. You can say, oh, this is the like a recurrence interval for this particular earthquake. And here you can say strain. So on the basis of you have a GPS and network, you can identify strain, and you can identify when earthquake may come on the basis of the strain. So here we have stress, you are starting, and here you have strain. So generally we observe the strain on the surface, and we can make out, okay, a particular zone, what is the recurrence interval of the earthquake, and how we can use the strain. On the basis of this, we can use for the earthquake prediction. Here, but this is not sufficient. It has more depth, research that everywhere earthquake doesn't come, because in interface we have some heterogeneous materials. Sometimes it is crystalline materials, and energy accumulates and that place only. And during earthquake, only slip was taking place that place only, and it is not randomly. So you cannot identify, you cannot say that everywhere earthquake may occur in the subduction zone. Only those places where you have asperity and barrier. People say it is a barrier because sometimes it has fracture zones. Because when on your oceanic plates, there are several small mountains type of structures, like a 2 meter, 3 meter. So when it goes in the subduction, when it goes in the interface, and it can accumulate energy. Like if you feel that sometimes if you go in the trekking and you see sometimes you have some blocks in the water flow. In the water flow, you have blocks, and in these blocks, like if some materials like soil comes and it deposited here in the front, and it when your water flows more, then it can take out in the flow. Otherwise, it will accumulate. Similar way in the case of aspertige also. So sometimes some ridges, sometimes some aspertige, it can block the like it can accumulate the energy. And when when your plates continuously it is going downwards and accumulating energy, when its strength is more than the strength of your system interface, it can break and it can provide the big earthquake. So on this basis, we can identify this aspertige on the basis of the numerical modeling with the GPS displacement. Okay, now you can see the aspertige model. Generally, earthquake doesn't occur like it is not homogeneous interface. It has heterogeneous material. So before earthquake, it start to lock, and once it's locked, the all system here you will feel that it is going down, and it may be like it can go like 100 years or 500 years. It may be 1,000 years during locking position. People say interseismic phase. It is nothing. You will not feel any earthquake, but suddenly earthquake will occur along the surface, in the locked zone, and during this period it goes up, and suddenly when it goes up, it can provide the huge tsunami, and it can provide the like a damage in the coastal region, and it is not good for environment. So for that, if you know with the GPS velocity what is going on these surfaces, it is going to lock or it is going to like slip. So on this basis, you can suggest, oh, this region is locked and it can provide the big earthquake. So here it is seismic cycle. Like once what happens, it interseismic, co-seismic, then interseismic. Again it goes co-seismic and interseismic. So what we say, because we see the deformation like a permanent, like if you see Himalaya, why it is going up? It is geological time scale. It was not like this. Yes,
sir.
Yeah.
Actually, we are still stuck at slide number 18. If you please shift F5, and then it will come on the screen mode, so that I think when you are changing the slide, we can also able to. Yes.
Okay. Mm-hmm.
Will you please change the slide?
Okay.
According to your talk.
Yeah.
Then only we'll understand.
Okay. Yeah. Okay. Correct. It is 28. So we have interseismic cycle. So what happens first time this cycle is identified by the Ray. So he observed the earthquake in San Francisco. So when you have like some earthquake, suddenly we have some permanent deformation, because Earth is not pure elastic. Like soil is not pure elastic. Once deformation takes place, and some residuals, sometimes subsidence, sometimes upliftment. This permanent deformation, so we can observe with it, because deformation is not pure elastic. It has viscous also, and this viscous material provides the permanent deformation. So sometimes if you see in the Himalaya region, and if you go in the Koina and some places, we can see some deformation with permanent. We can observe it. So here we have like how we can work for the identify the like earthquakes. Like we have like subducting plate, we have GPS site on this, and we have to this during the earthquake co-seismic. So earthquake occurs here, and we make the like some numerical modeling. We like make the several geometry, like a small patching of the geometry, and use the green function, and we have displacement, and we use the inversion of the displacement, and on this inversion of this displacement, we can identify how the slip has taken place along the megathrust along the particular fault zone. On the basis of this, we can also identify the interseismic locking. This is the totally inversion methods which we use for the particular zone. So here, by using the GPS displacement, we have several GPS in the Chilean region, and we have observed several like you can see like black and yellow like colors map here. You say it is locking. Like 1 is perfectly locking, 100%, and 0 is nothing locking. So if you see the very like a different way, so if you see the small region here, if you see here, so in this way, if you see the different earthquakes here, like here it is the 2014, this is 2007, this is 1995, this is 2015, this is 1850, this is Mauli earthquake. So if you
Sorry,
see
sir. Sorry, sir. Sir, which slide are we talking about right now?
23.
Sir, we are not on 23, sir. We are still on 21. It's not moved. Yes,
Oh,
sir.
sorry.
Thank you,
Yes.
sir.
Also play from current slide. Please play it from current
Please
slide.
play from current slide. Click, karo, sir. You can click on play from current slide. Yes, sir.
So now we have several earthquakes. Are you able to see this? Locking degree from GPS data in Chile?
Yes.
Yes, sir. But it might stay the same if you don't move it.
Okay,
So play
correct.
from current slide. If you click that
Yes,
button, yeah, please. Thank you. Thank you, sir.
play from current side. Okay. So here we have several patches, and we observe that we have a very nice fitting with the earthquakes in the locked zone. But problem is how big like if you see in this region Taltal here, we don't have very good GPS network, and it had very bad resolution. So we have to, if we are using good data setup, we can have the good locking model, and we can suggest, oh, this region has the big locking is very big region, and it can provide the big earthquake. And in this basis, we can see in the Tohoku-Oki earthquake 2011. So if you see the locking model, locking degree, it was 100% locking was in the front of the Sendai, and we have big earthquake like a 9.5, and these were 2003. So on the basis of this, we can say this locking model is the very good suitable for predicting this which region may have the big earthquake. In the similar way, if you see the Nepal earthquake, we have like a very dark here color. So generally earthquake occurs here, and and there are several phenomena why earthquake doesn't come in the like a subduction earthquake, and why not bigger earthquake occurs in the Himalaya region. Because I already told that this type because it is a continent collision, and its strength is very less, and it cannot sustain more stress, and it cannot provide big earthquake. But if you see that it's if you try see that it is two plates, one is the Indian plate, another is Eurasian plate. But Indian plate you cannot see more than 40 kilometer, because it is the continent same density material. It doesn't support for the going down. It start to build up, folding, and it start more stress is providing the upliftment of the Himalaya. It is not supporting for the earthquakes. That's why we don't have big.
Sir,
Yes,
are we at the 26 slides? Sir,
I am.
can you do one thing? If you can if you can see the lower panel, there is a full screen mode. After the, 4 dots are there. If you can click, I think
Sorry?
it will work. Can you see the
Which?
lower panel? Lower panel. The
Mhm.
lower panel near to 4 dots. If you click on
Yeah,
that, I think it will come as a full screen, and
full screen. Yeah,
we'll be able to see the full screen.
but
That's not coming full screen.
just wait.
There is an issue.
It is okay.
No, so far no.
And
I'm
then
at
again,
the lower panel. At the lower panel,
yeah, I see
near to 4 dots.
three dots is
There are
there.
4 dots are
So in
there.
this, I am looking full screen, uh, but I am not able. It is not able to see my presentation.
No,
More
so far
options.
no.
Just wait.
No, we are at Yeah, we are at 28, slide number
This
28,
is 24.
but not the full
It is
screen.
co-seismic slip and pre-seismic locking degree. Are you able to see?
Yeah, yeah. We are at 24, but I think when you go to
Yeah, yeah.
25,
So
we are
now
not
it
able
is
to follow
25.
you. So
With respect of
right now
value.
we can see. No, 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 no. We are not at 25 right now.
Oh, I
Something
will
wrong with this.
stop the presenting again. I will stay.
Ah, right now we are at 25.
Now to it is Patman Susi. Can you see it? Jayant.
Coming. Ah, yes. Yes, yes. Now it's fine. Not the full screen. Just again the slide.
It is visible now.
Yeah, it is visible, but not the full screen. It's just a slide.
Oh, I because it was.
It's visible. Can you see that there is a lower panel? Yes.
It is visible now.
No, no.
Just wait. Now it is. It is visible, Jayant.
Yeah, it's coming. We haven't seen it yet.
Okay. May I start?
No, sir, it's not coming
Okay.
so far.
Just I will send the slides to you. You can just try to share with me. It has problem with something. It is not going proper way.
Yeah, we can see now.
It is okay, Jayant?
No, sir, so far we haven't
So,
seen. It's coming up.
Jayant, I just shared. Just I send my slide to you. Can you try from there?
Yeah, let me check.
Yeah, please try from there.
Yes. Just wait a minute. 1 second. Okay. Uh, let me share my screen so that you will be
Yeah,
able
okay.
to see.
Yeah, yeah. I just I'm stopping my presentation.
Yeah.
Yeah.
Can you
Yes.
see now?
Okay. Yeah, yeah. I am able to see now.
Can we all see now?
Yes.
Yes, sir.
So, yeah, yeah, correct. So, just to go in Nepal region, Nepal, it was 26 something. Go ahead.
Ramam, can you see now?
Yeah,
Yes, sir.
yeah,
We can. We can.
yeah, 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 just you.
Ah,
Next, Jayant. Yes. So now, Jayant, when I will say next, you can put next one. So, okay. Now we are going, and I would like to explain something like a Indian scenario. What is the earthquake scenario in the in Nepal and Indian region? So, if you know that this is the like a we have very good seismic record, like last around 250 years ago. So now we can see that most of the earthquake occurred in the Indian like Indian erosion collision zone. But there are several big earthquake, like a not big,
yeah,
but
yeah, yes, sir.
6.7, 6.1 bigger. It is the crustal faults, and this earthquake is very, very like dangerous because its intensity is very like high, like more than 8, and it has a lot of damage. So now, if you see the in the Indian recent collision zone, okay, you know that in collision zone earthquake generally used to come. Like in Delhi, people are used to feel several times earthquakes. And you know, in the Delhi, we have Delhi Arauli like ridge. It's subjected toward the Eurasian plates. And when it has, like already I told that some heterogeneous material are there. Like if, just next one. I will, yeah, okay, okay. So in this case, you have like a very good correlation with the earthquake. You have that white patch. It shows the plane of the earthquake. In this, you can see that red, highly red, dark region, locking region is like 100%. Only earthquake had occurred that region. And just put next one. Okay, so what happens in the during my PhD, I have worked for the gravitational potential energy of the Himalaya region. I worked as a PhD student in the Mumbai in the Indian Jubilee area. So there I have used the gravitational potential energy because once you have like a putting mass like more mass on the surface and it is pushing towards the downwards because it needs some equilibrium. So once we have putting more mass, so it is pushing more stress toward the sidewise. So similar way we have buoyancy forces and gravitational stresses. So in Himalaya, it is going up without doubt, but it is pushing out towards the downwards. And due to downwards, it is supporting some vectors horizontally. So in this way, we are going to have some stress sidewise. So this is the gravitational potential energy, which is very, very important for the earthquake study also. So in this, we can identify what is the region along the coastal, like along the boundary, which can have big earthquakes. So in the case of the Himalaya region, next, yeah. So here we have modeled the gravitational potential energy, and if you see this in the case of the boundary, we have one like a 3-4 patches. Here we have Bay of Bengal, here Assam. This is in front of the Nepal, and here we have like a Tapovan area, and we have like a here like a Delhi region. So this region has the low gravitational potential energy, and where you have low and another is very high, so it is pushing toward stress. It will be more high in between. So that's why we observed Nepal earthquake watch in that gradient region. So already we have published this paper in the 2013. So because wherever we have like a high maximum gradient of GP, that region would be more stress. And this, due to more stress, like energy will accumulate that region more, and it can like break with the earthquake. That's why we observed the 7.9 and 7.3 both earthquake was in our range where we are predicting in beginning. So now we have like a second patch here. If you see this second patch, it was west of the Nepal. But I am not an authorized person to say, okay, earthquake is going to come when and what is the time. I cannot say, but I can suggest this region is next like a region to have the earthquake. But don't be panic. Earthquake may not go more than 8 because this is the subduction. This is not subduction zone. We have only 2 continent collision, and its strength is not much. It cannot survive. It cannot accumulate more energy, and it can break with the normal like a 8. It cannot go beyond 8. But most of the energy it useful for the upliftment of the Himalaya. But you may ask, until what time Himalaya will be upliftment, when it will collapse? Because you know, when India was separated from the South America, Africa, Antarctica, its velocity was 180 centimeter per year, and its velocity was reducing very, very fast. Now it is around 33 millimeter, 3 centimeter. So in this way, we have velocity is reducing. Why? Because you have big block, it is Himalaya, and you have big mass, and it is not supporting to go Indian plate towards the downwards. So that's why we are thinking that this type of seismicity is going to reduce, because it is going to collapse, but it is geological time scale. But still, we think that we understand that this region, arc region, has the like a possibility to have earthquake around maximum 8.5, not beyond this. And another one, if you see the like Delhi region, like if you try to see Delhi region, we have like Arauli and Delhi ridge, and when it goes towards the Inversion plate, it has some materials like if you have some upliftment, it has some like density, several like a dense, some heterogeneous material. It has different density material, so it can provide some transverse faults. That's why if you see that in the Delhi region, we have a small earthquake like 2.5, 3.5, 8.5. It cannot go beyond 6 in Delhi. So I observed last 2 months there's so much like a panic. It was like a several earthquake, and people observe it. And another one thing more. So next, can you please? Okay, in this I am trying to study some more depth in this region. I use the, because when I worked during my PhD in 2013, so I used the like a Topo 30. So it was the resolution was not good. So now I am trying to use the SRTM 30 meter. So like every 30 meter we have elevation data. So on the basis of this, we can make more better result. So in this, we observe that both earthquake, like a bigger main shock of the Nepal earthquake 7.9 and 7.3, both was in the highly gradient region of the GP stress. So if you have like a GP, one place is 10 unit and one place is like minus 10. So if you have see the gradient, it has more stress region. So in this way, if you have high gradient of GP, that region can be used for proxy for, okay, this is the places which can have the big earthquake. So this can be used for the our understanding. So if you go just go in next. Okay, so here we plot the topography map and the GP map. So in this, in the we have like here a topography and we put the GP, and here we are putting GP and here deviatoric stress. So deviatoric stress means we take the gradient. On the basis of gradient, we see that we have like a sudden change of the GP has the highest, like maximum, you cannot say somewhat maximum stress in this region. That's why earthquake occur in that region. So now if you see the my previous 2013 result, again can you go 2013 GP 2 slides before? Yes. So in this, if you go in this region, now I think my opinion, second region west of the Nepal, like if you see the Nepal, it is like a main site, like a Kathmandu, under the Kathmandu epicenter was there, and now earthquake is going to propagate, it like initiate into where the west of the Nepal, and that region may have the 7.8, 8.0 earthquake. So that region is the very suitable for the next future earthquake. Okay, then next. Yes, here I try to explain a little bit more. In this, we have like a arc region. So in this, we have several earthquakes, like 1950, 17, 14, 1934, the Bihar earthquake, 2014 was very less, like a range was like a rupture was very not very big, and we have 1505, 1803, 1905. So now next earthquake, I have realized that it was 1505 region here. This is the, I think, next one may have the earthquake, but I cannot say when. This is the limitation of our technique. And we have like a 2005 Kashmir earthquake, and this is the like a scenario. We cannot say when earthquake will come, but on the basis of locking with historical earthquake and on the basis of the regional structure, we can say that earthquake, where earthquake may occur and how much big earthquake can take place particular region. Okay, then next one. Okay, here I would like to explain a little bit about the Delhi region, because if you see in the structure, we have like a arc region. It is the collision between like a collision of Indian Eurasian plate. If you see here, you have the like several earthquake in this one. But I am interested to talk about the Delhi Haridwar. So people say Delhi like Arauli also. It was Delhi Arauli, the Delhi Haridwar region here, and we have like a Faizabad region here, another region. So I am interested to discuss about this Delhi region, because you have like people say that while like one plume three was there, like when Indian plate was like separating from Antarctica and South America and Africa. So that time it was passed through hot spots. When it was passing a hot spot, like magma was coming in the some like a circular like a shape is there, and it was very big circular shape, and it was like magma used to come up, come down, come from down, and it like comes up. And when it was passing through the that region, Indian plate was passing that region. So what happens? It just passed, and it just like if you have a banana leaf and it can slip, and it become like a thing. It's a low velocity zone. So in the northwest of the India, it has low velocity zone, and due to this, if some earthquake comes in the Afghanistan, Iran, Iraq, Kashmir, you will feel in Delhi feel a lot of vibrations because that region is low velocity zone. Automatically, you will feel some shaking, but don't be like it's not very dangerous. And the problem is it is shakings. And in the Delhi itself, there are one region which is going to which is subducting in the Russian plate. We have Delhi Haridwar ridge, and it has different density material. So when it has some density material, it can slightly transverse. So in this way, we have like a smaller magnitude earthquake. Okay, Jayant, next one. Okay, so what is challenge? Because we can use any precursor with like a 1 week something. So for that, we have to go for the short time information. So for short time information, we have to use the some radiation and detection instrument, and some like some wave detection instrument, which can be used for the like understand okay, when earthquake is going to occur. For that, we have to identify particular place where earthquake is going to occur. Like some places, we we keep some instrument some particular place, and earthquake doesn't come in 10 years. People feel, oh no, this is the bad decision to put the instrument there. So for that, people should be patient, should keep the instrument some places where like don't worry about time. Like if you keep some instrument for 10 years, suddenly earthquake may come after 5 years, 10 years more. So in this way, it needs patience and need to continuously monitor. And because radar measurement is very good proxy, but problem is only it can identify 10 kilometers. If you want to measure the earthquake in Delhi, so you have to install more than 100. Then you can use it, but you don't know earthquake when it's going to occur. So for that, we need continuous measurement of this type of instrument, and we should have patience. Sometimes it can provide better information. Otherwise, if we can put the in Himalaya region, because in Himalaya we can get 2.5, 3.5, 4.5 earthquake frequently. So in this way, we can identify those information from radar measurement. But in the radar measurement is not suitable for subduction earthquake, because earthquake comes in the coast, it is far from the coast and in under the water, and it cannot provide, because earthquake comes 60 kilometers away from the coast. Your instrument, you cannot detect, it is not a resolution that good of your instrument. You cannot get that information. So that is the limitation. So another one, we don't have exact radiological information. Like we are numerical modeler, so we use the, like sometimes we use the pure elastic, sometimes we use the viscoelastic, but it like in beginning, like now we are trying for viscoelastic. In beginning, people use the elastic body. When you thinking that the interface was pure elastic, so your energy will be different. So it is necessary to have the exact radiological information of the particular zone. If you know the proper radiological information, then you can your prediction will be good. Otherwise, you are you have calculations, several calculations. You understand this much energy, but exactly this is not, because it is not supporting like elastic body is not there, and it has some viscous part, and your energy, like you are thinking that it is 10 Newton meter, but it is only 6, 7. So in this way, you cannot predict exactly. So other crustal faults. So because there are several crustal faults, but it is you cannot observe on the surface. So it is important to identify those features. So you can, once you identify those faults, those features, you have to concentrate on that and try to see what is the slip rate on that fault. Then you can go for the better prediction for the seismic hazard. So it needs more depth like a study and more best sensitive instrument for the seismic hazard assessment for the safe environment. Okay, thank you. If you have any question, please ask me. I can go for the answer and question and answer.
Thank you so much, sir. Though time constraint, you have dealt with each and every aspect of the topic precisely. So thank you so much for that. I request all the delegates, if they on and students, if they have any question, they can drop it in the chat box. Those will be read out and will be answered by sir. Or you can reach out to us through mail with the consent of the speaker. Will revert back. So we'll wait for 2 minutes. If they have questions, they'll drop it. Otherwise, we'll conclude the session. Yeah, so the people who, if you have any queries, I request all the delegates again, if you have any query, you people can just drop it in the chat box. So yeah, here we have one question. How do we identify the origin of an earthquake, sir?
Yes, like after earthquake.
Yes, so the question goes like, how do we identify the origin of an earthquake?
Okay, correct, yeah. So, because when earthquake occurs, it radiates several waves, seismic waves, P wave, near waves. So, we have several global, like a teleseismic network. So, like once you receive any signals, you can identify how much distance. So if you have the triangulation method, if you have minimum 3 seismic network, P wave and S wave, it can identify. If I am in the dark light, I say hi, so nearby person will listen me, and they understand how much velocity of seismic wave, and by multiplying time, they can identify how much distance. In this way, we can use this information for with the triangulation method where earthquake has initiated. This is seismic network provides. It is triangulation method, simple. How many earthquake? Oh, okay. Okay, Sami Dalvi had asked about the how many earthquake zones in the India. So you cannot say number 1, 2, 3, 4. Like mainly you can say in the arc region, it is the collision zone. It is one type of earthquake. It is like collision zone earthquake. But another one is the crustal earthquakes. Like you have Koina, Latur. So this type of earthquake also very effective. So you have to understand two in the Indian region. One is the arc region, like if you have earthquake Nepal, Bhutan, and Assam and Kashmir. Another is the away from the arc. Like somebody say that in the Delhi earthquake may come 8 magnitude. No, but one thing more. Delhi is around 150 or 200 kilometer from the arc. If any big earthquake come in the arc 7.9, you will feel shaking in the Delhi also. So don't think that earthquake comes in the arc region, you may feel shaking in the central India also. So that is not a thing. Okay. Anybody more?
I think so. That's what we had, and people are thanking you for the informative session.
Okay, thank you.
Yeah, so thank you so much for your, yeah, sir, we have one more question from
Yeah.
Nandeshwar
What is the
in the
reason
chat.
behind the Nisarga cyclones change? Is oh sorry, this is out of my scope. It would be wrong if I say something because I am not expert about those things. I don't work about the cyclone. It has like another topic.
Okay, so I would like to request Ramya ma'am to come forward and propose a vote of thanks in order to culminate this session of the day. Thank you, everyone.
Thank you so much, Ashwini ma'am. Hope I'm audible.
Ma'am, yes, ma'am, you're absolutely audible. Yeah.
Thank you. Thank you. Charles Curlett quoted, "It takes an earthquake to remind us that we walk on the crust of unfinished planet." Honorable resource person for the day, Dr. Maheshan Srivastava, respected dignitaries presiding the event, respected delegates from all over the country, dear colleagues and students, a very good afternoon to you all. It's a matter of great pride for me to propose vote of thanks on this special occasion today. I, Ramya Madan Gopal, on behalf of Pillai College of Arts, Science and Commerce and Internal Quality Assurance Cell, would like to extend a big thank you to our guest of honor, Dr. Maheshan Srivastava, Assistant Professor, Northern Catholic University, Chile, and Investigator, National Research Center for Integrated Natural Disaster Management, Chile, South America, for his in-depth analysis of the content and organized and vivid presentation on the topic Seismic Hazard Assessment, Prediction and Challenges for a Safe Environment. Sir, we are indeed grateful for an indulging, inspirational, and a thought-provoking session on environmental hazards and impact of earthquake, which is truly the need of the hour. Thank you so very much, sir.
Okay.
We would thank you, sir. Thank you.
Okay.
We would also like to acknowledge our deep sense of gratitude to our dignitaries of our parental organization for their support throughout to organize and conduct the webinar in best possible platform in such challenging global scenario. We would also like to sincerely thank delegates from all over for their overwhelming response and active participation, which made the session lively. We look forward to your cooperation in our future endeavors. Thank you so much for being our inspiration. We've been fortunate enough to be backed by very motivated and dedicated colleagues and technical supports. Thanks to Pillai College of Arts, Science and Commerce family, from our principal to vice principal to teaching and non-teaching staff members whose contributions and cooperation played a big role in organizing this event. Once again, I want to state that we are most grateful to all our invited guests. Thank you for being with us this afternoon. It's been a great pleasure. Thank you all. Until next time, take care and stay safe.
Okay. Okay, then everybody, thank you very much for giving me this opportunity. It was very nice interaction with all of you. I am ready with next session anytime. Whenever I will visit in India, I will like to have the interaction with all of you. Okay, thank you. Bye bye.
Thank you, sir. Bye. It's been our pleasure. We would like to conclude the session. The feedback link is already shared. Thank you all.
Ajay, please stop streaming.
Yes, sir.